In 1926, a reserved student from Bristol quietly invented the mathematical language behind quantum mechanics. 2 years later, Paul Dirac's shocking new equation would upend what physicists thought they knew about electricity itself. His insights bridged Einstein's relativity with quantum theory, foreshadowing discoveries that would transform the modern world. But what exactly did Dirac see that no one else could? The answer begins with the unusual mind that rewrote the rules of science. Paul Dirac was born in Bristol in 1902, the son of a Swiss father and an English mother. His childhood was shaped by strict discipline at home. His father, a language teacher, insisted on precision in both speech and thought, a habit that would stay with Dirac for life. At school, Dirac excelled in mathematics and science, but he did not stand out socially. He spoke rarely, often giving only the briefest answers. This quiet intensity would become his signature. After finishing secondary school, Dirac studied electrical engineering at the University of Bristol, earning his Bachelor of Science degree in 1921. Engineering suited his practical mind, but he soon found himself drawn to the abstract world of mathematics. The post-war economy left few jobs for engineers, so Dirac returned to Bristol to study mathematics, deepening his understanding of the logic and structure behind physical laws. In 1923, Dirac won a research scholarship to St. John's College, Cambridge. There he came under the guidance of Ralph Fowler, a physicist known for his careful approach and encouragement of original thinking. Fowler recognized Dirac's unusual clarity and independence. At Cambridge, Dirac's disciplined habits and engineering background merged with advanced mathematics, setting the stage for his later breakthroughs. The transition from Bristol's practical workshops to Cambridge's theoretical halls was not just a change of scenery. It was the forging of a mind that would demand precision from nature itself. By 1926, Dirac was no longer just a promising student. He was becoming a builder of the mathematical language that quantum mechanics would use for decades to come. His doctoral thesis at Cambridge, completed that year, introduced a new way to handle the strange algebra of quantum theory. Instead of ordinary numbers, Dirac worked with operators, mathematical objects that could represent the act of measuring position, momentum, or energy. This operator algebra allowed physicists to describe how particles change and interact, even when the rules defied classical logic. To keep track of these abstract calculations, Dirac invented a new notation. He called it bracket notation, a system that writes quantum states as angled brackets, with the left side, the bra, and the right side, the ket, standing for different aspects of a quantum system. This compact language made it possible to express the rules of quantum mechanics with unprecedented clarity. The notation appears in his 1930 book, but the seeds were already present in his earlier work. Dirac also unified two competing approaches to quantum mechanics: Heisenberg's matrices and Schrödinger's waves. Through his transformation theory, he showed that both were different views of the same underlying reality. This breakthrough made the new quantum theory more flexible and powerful, opening the door to further advances. In parallel, Dirac tackled the behavior of electrons in dense environments. Working independently from Enrico Fermi, he developed a statistical law now called Fermi-Dirac statistics that describes how particles like electrons fill up energy levels. This principle is essential for understanding the structure of atoms, the properties of metals, and the stability of matter itself. By the end of the 1920s, Dirac's mathematical toolkit had become indispensable for anyone working at the frontiers of quantum physics. In 1928, Paul Dirac set out to solve a problem that had stalled the progress of quantum physics. The existing equations could describe electrons at low speeds, but they broke down when the effects of Einstein's special relativity became important. Dirac insisted that any equation for the electron must treat space and time on equal footing, just as relativity requires. He also demanded that the equation be linear in both time and spatial derivatives, so that the evolution of the electron's wave function would be smooth and predictable. This combination of quantum mechanics and relativity forced Dirac into uncharted mathematical territory. Ordinary numbers would no longer suffice. Instead, he introduced new mathematical objects, matrices labeled alpha and beta, which could encode the necessary relationships between space, time, and energy. These matrices could not be chosen arbitrarily. Their algebra had to guarantee that when squared, the equation would reproduce the correct relativistic energy formula. Energy squared equals momentum squared times the speed of light squared plus mass squared times the speed of light to the fourth power. The only way to satisfy these constraints was to use 4x4 matrices. This meant that the electron's wave function itself had to have 4 components, a structure known as a spinor. Unlike the single-number wave functions of earlier quantum theory, spinors naturally included the possibility of electron spin, a mysterious property that had puzzled physicists. In Dirac's formulation, spin was not an extra feature bolted onto the theory. It was built in from the start, a direct consequence of the mathematics required by relativity and quantum mechanics together. With these tools in hand, Dirac wrote down his famous equation. The alpha and beta matrices acting on the 4-component spinor described an electron that obeyed both quantum rules and the demands of relativity. This new formalism did more than just patch the old equations. It revealed hidden layers of structure in the electron, and it pointed toward the existence of entirely new forms of matter. Dirac's new equation, though bold in its ambition, faced an immediate test. At low speeds, far from the extremes of relativity, it had to match the well-established results of quantum theory. In this regime, the equation reduces to a familiar form, and it predicts the electron's magnetic moment with a G factor of exactly 2. This result, first obtained by Wolfgang Pauli through a separate, less fundamental approach, had been confirmed by experiments on atomic spectra. Dirac's equation, built from first principles, reproduced it as a natural consequence, and no extra assumptions were required. This agreement was more than a technical detail. For Dirac, it was a sign that the mathematics was on the right track. He often spoke of beauty in equations, insisting that it is more important to have beauty in one's equations than to have them fit experiment. To him, beauty meant logical consistency, economy, and a sense that the pieces fit together without force. This was not a matter of taste, but a guiding principle for discovering truth. In his 1963 lecture, he made this creed explicit, and it had already shaped his work decades before. Despite this confidence, Dirac rarely boasted about his successes. He was known for his reticence, offering only the briefest comments even when his predictions matched experiment. Yet the quiet satisfaction was unmistakable. The equation's success with the G factor and its precise prediction of the hydrogen atom's fine structure gave Dirac reason to trust his approach. The mathematics had passed its first empirical hurdle. Now the stage was set for the equation's most surprising consequences. They would challenge the very foundations of physics. Dirac confronted a puzzle at the heart of his new equation. The mathematics allowed for electrons to have negative energy, a possibility that threatened to unravel the stability of matter. Instead of discarding these solutions, Dirac proposed a daring idea in 1930. Imagine a vast sea where every negative energy state is already filled. According to quantum rules, no two electrons can occupy the same state, so ordinary electrons cannot fall into these lower energies. Only a vacancy, a missing electron in this sea, could behave differently. This absence would act like a particle with the same mass as the electron, but with opposite charge. He called this the hole, and in 1931, he predicted it would appear as a positively charged electron, later named the positron. This sea metaphor did more than patch a mathematical oddity. It set the stage for the experimental search for antimatter and redefined the boundaries of what physics could expect from nature. On a summer day in 1932, Carl Anderson was studying cosmic rays with a cloud chamber at Caltech when he noticed a curious track. The path curved in a magnetic field just like an electron's, but in the opposite direction. Careful measurement showed the particle had the same mass as an electron, yet carried a positive charge. Anderson had found the positron, a particle Dirac's equation had predicted a year earlier. The photograph captured a moment when mathematics and nature met in a single undeniable fact. For the first time, a new form of matter, antimatter, was not just a theoretical possibility, but a reality. Dirac's abstract reasoning had pointed to a particle no one had ever seen, and now there it was, etched in silver vapor. The confirmation was immediate and profound. The foundation of quantum field theory gained its first experimental cornerstone. The Dirac equation still shapes every quantum device and particle discovery today. As technology pushes further into the quantum realm, Dirac's vision guides the way. Our world runs on principles he revealed, reminding us that pure thought can transform reality. What possibilities will the next insight unlock?